Thank you for attending our session today on Inventor for the Wood Trades. My name is Steve Whittam, and I represent Whittam Associates. Whittam Associates has been a support arm of Autodesk for the last 28 years, specifically working with woodworkers throughout the US and Canada. Today, our goal is to provide solutions, methods, workflows, and technology that will assist all to become more productive utilizing the existing tools that are available. Thank you again for attending our session today. In our session today, we decided on selecting a very recognizable mission table. We did that because the complication of the joinery, which were plug tenons, high hidden tenons, as well as dovetails on the fascias, added a tremendous amount of complication for a normal user of an Inventor. This table, start to finish, is approximately 15 minutes worth of work, and it's my hope today to show that capability. So let's get right to the model. I'm going to start out with a brand new standard part, and I normally, in something of this nature, will create the table surface. You'll also notice that when we start working with dimensional information, I'm usually using some form of a parameter like tabletop thickness or table diameter. And the reason for that is whenever you start a job, it's going to change. And the more variability that you put into the model in terms of control of variability, the easier it is to manipulate it after the fact. So I've never seen a job start and finish and have no changes to it. So again, what I'm doing here is I'm basically building off of the table surface the fascias themselves. But because the fascias are individual pieces, 4 separate pieces, I'm going to break that fascia up into quadrants. Now, I am using solid body modeling here. It's one of the simplest and easiest way to get the most out of the utilization of Inventor and the quickest. It has its positives and negatives, but I hope to show that during our session today how simple this will become. Of course, I'll be trimming this up, and I'll be extruding the fascia to a height of 2-3 inches, and of course I'll give it a variable name, fascia height. And these will really be used very effectively downstream when we tie it to an iLogic form. Now, of course, in this particular situation, I am using solid bodies. Okay, so as I start extruding things, I'm always going to be saying it's a new solid body. And of course, I can share the sketch if necessary also. So again, it frees up a lot of time. Now, once I have my basic environment of one leg and one fascia, I then pattern them. And when I pattern it, I'm going to pattern it to get new solids. So you can see that at this moment I'm up to 6 solid bodies, which will, of course will become individual parts when I'm done, because I do have to machine this. At this point I can rename them as I'm indicating, and there are many tools in the marketplace today that are free that will help me do this without us touching each and every one. Okay, once I have the legs done, then I can go back and I can do a pattern of the fascia themselves. And again, I'm doing exactly the same thing, where I'm going to indicate I want 4 of them, and they're new solid bodies, and it's just growing. Also in the browser, you see I'm showing extended names. So I see it's a new solid rather than a join. Well, again, testing the water as I go, I see that I have everything that I need. So again, I can change visibility, I can turn things on and off. It's almost like it was a full assembly. Okay, once this is done, we can start having a little bit of fun now with it. In any of our entry-level classes that people start getting involved with design, they want to change things quickly. You know, maybe it's not big enough, small enough, wide enough, whatever the value is. So we always recommend people to start getting used to the usage of iLogic. And what I'm doing at this point is I'm showing the capability of iLogic, the simple capability where you can take all of those variables that we've already created, change the form name, and have this control our model. Okay, so what I'm doing here is I'm just labeling the name of the form, and you can see on the right hand side the label now is dimension for table, and changing some of the buttons in the form itself. Again, very simple, straightforward tool that can be used, almost on anything one builds. The form can be docked, or it could be floating, and as you see, I'm going to be changing some values, and the model is changing. Now, yes, it is a single part at the moment, but this will also control the assembly when I'm done. So, for a little extra effort up front, this goes tremendously a long way. And I highly suggest everybody take a look at this when they get back into the office. Our next step in the model is to put a center leg. Because I'm working on a circular part and I'm sketching on a circular part, I automatically have a center point being designated. And using a center point rectangle and assigning it the dimensional information, again, it becomes quite simple. Also, I'm going to apply an extend to and a new solid so that the dimension for the table in the iLogic environment now controls the height of that leg as well as the outside legs. We're now ready for the supports, the stretchers that are at the bottom and at the top of that particular table. So I'm working from the bottom side, and I'm putting a center plane right down the middle of the table and drawing two sketches, one for the top stretcher, one for the bottom stretcher. And because it's a solid body, I can use constraints, 2D constraints, collinear constraints, so I can line things up very, very quickly. Again, I'm using the same parameters that I've used in the previous sketches. So they are not global parameters at the moment, they are all part parameters. And again, this makes it quite quick to generate this information. Now, if I need some detailing, okay, put some filigree, change something, manipulate it, give it a little bit more oomph to the presentation. Of course, using quick sketches, as I'm showing here, as well as dimensioning the sketches to get exact accuracy I'm looking for in a sketch like this is quite simple. Once I have that, because I'm on the center of the table, I'm going to extrude this using midplane, and then of course listing the parameters so that I could say thickness, okay, because they should equal the fascia thickness. Can quickly create that bottom stretcher. Now, of course, it was in the same sketch, so by sharing the sketch, I can quickly go to the top and do almost the same thing. Now, like we did on the fascia, I'm going to rename this, and then after I rename it, what I will then do is do a pattern and create more solids, more solid bodies. Now I know that I haven't done any joinery yet, and I don't like doing my joinery until I've got it accepted as a go. Why put extra effort in until I know exactly the size, the presentation, what the client wants, because obviously they might change it a couple of times. But in the native way of using Inventor, that would be very difficult. And again, today I'm hoping to show a whole different way of approaching this. So I'm finishing up naming solids, and these will become the part names. So if they're going to go out to machining, this is the information that'll go with it, of course. And they can be turned on and off, visibility and so on. But I can start having a lot more fun with this right now, because everything I've just done is now controllable by iLogic. by the iLogic form, I should say. And if you can see that the same form that I used previously, I'm changing this table dramatically. And it's adjusting. It's not adaptive. There are no 3D constraints on it. It's very, very fluid at this point as a design study to make sure that it is accurate and what my client might want to consider here. So again, every single part of it down to the thicknesses of the materials are adjustable. We're now at the point of turning our solid body part file or a multi-body part file into an assembly file. We have 18 solid bodies. We've named them. They all are sitting in the browser. And if we go back up to the top menu and pick Make Component, we can highlight all of them. And as you can see, we are going to rename them into individual IPT files. At this point, we created an assembly. The assembly is all grounded together, fixed. There's no 3D constraints on it at the moment. There's no joinery on it at the moment, but they are individual parts that could be machined at this moment or could be documented at this moment. The one thing that we like is the ability to still use the iLogic form that's in the part file to control the assembly. So if a project manager says, you know, it should be this big or this small or this high or this long, by changing just a couple of values, the entire assembly just changed on me. Standardizing the way we do things. As you can see, we still have single parts. There's no joinery yet on that single part, but we're going to be moving in that direction shortly. We also have a tool set that we like called Woodworking Design. And Woodworking Design allows us to start applying materials. Grain direction, different materials, composites, edge banding, and the like, not only to get a visual, but also to get a correct cut list out of it. Those fascia boards, you know, they might have to be cut out of solid stock. So what would be the actual size of the solid stock before you cut? Again, they could be strip laminated. There's lots of different ways, but I'm building everything out of solids right now, just as the example for today. And again, I'm just changing a couple materials here and there, and all of this is fully customizable for, again, any materials you might use. Visualization is a lot nicer to look at than gray. And of course, you can see they're all individual parts. Now, the other thing we like about this is that we can go to a bill of material, a cut list. Now, you saw the way I created this from the start. There was nothing that was unique, but you could see that every part is labeled, length, width, and thickness of every part is labeled, and you'll see the fascia boards look like they have to be cut out of a 3-inch by 31 by 6.88 thick part, you know, maybe on a bandsaw or something, as a rough cut to be able to accomplish this particular goal. If we built it differently, then of course the cut list would be different also. There are times where when we're building things, we forgot to do certain actions. And one of the actions is that I forgot to put a variable for the height of the bottom support. Right now it's just set to 6 inches. But I really want to say it's height of support. In other words, I want to add a variable because I want to control it after the fact. Again, utilizing iLogic forms and normal Inventor workflows, we can go back to the original model, which is that part file with the solid bodies, change it, open up the iLogic form, and then drag over the new variable. We can also just click on the variable and give it its own name that is a little bit more meaningful, with spaces in it, so that they show up better in the menu. And then once I've done that, I can just go back in and say it's, instead of 6 inches, it's 3 inches, it's 2 inches, it's 5 inches, and start controlling it. Now, I am on the part file right now, but again, whatever you do with the part file automatically will transition to the assembly file. So it's almost, you can build it on the fly any way you desire. So we've created a model, and it seems like everything's working just fine. Logic is controlling size. It could be ordered any size and dimensioned any way we want. We can create fabrication drawings of it. It's pretty well done, except that we can't build it because we have no joinery. And joinery is absolutely essential in the creation of furniture. Whether it's cabinetry with dowels and biscuits, or whether it's high-end furniture with mortise and tenons and dovetails, it's something we have to do. And many of our users shy away from it because it's a lot of work. Well, I think the game's changed, and my hope is to show that today, how quickly one can create this and how quickly we can standardize it so everybody can do this with really minimal work. Okay, so obviously we need some joinery here. I showed some pictures of the different types of joint. I'm looking at this table, trying to decide on what do I want to do. Maybe be non-traditional now. It has to hold up. It has to have strength. We have these stretchers that have to be attached to the legs. We've got 4 of them, and at least there's got to be 8 or so joints here that we have to deal with. Right now things are butt together, will not hold. I don't want to use screws. That would really wreck this. So I'm going to do a sliding dovetail. A sliding dovetail, I don't even need a clamp. So what we did is we created a whole different workflow in terms of adding this information. What I've done here is I've created a dovetail, an actual part that's independent of everything else. This part has 2 pieces on it, 2 solid bodies. One body is going to cut the tail, and one body is going to create the tail. I'm also using a different way of constraining. I'm using iMates with a dialog box where it prompts the user to select the face you're cutting into, select the top of the joint, and select the face of a piece that it'll then center it right in that rail. And you could see that that dovetail actually went perfectly centered into that with no trouble whatsoever. No constraints, everybody does it the same way, standardizing the entire engineering department. Now, I'm now going to do it, I'm going to put 2 tails in at once. So it's asking me to select the faces I'm cutting into, select the top of the joint, and now select the face. And it'll put 2 dovetails in. Again, consistency in what we do throughout the department will standardize the way people build solid models so that we don't scratch our head when we get somebody else's model and we can't figure out what they did, and it takes us too much time to just rework it. Okay, so we'll move down to the mortise and tenon joints. The bottom stretcher will have 2 mortises, 2 tenons. There will be a through tenon on the outside leg and a blind mortise or blind tenon on the center leg. So we've created an eye part that will have the capability of fully adjusting to any condition that has a mortise and tenon joint. Again, these are eye parts, so that just like any other eye part in Inventor, you can control every aspect of it. Now, I know that the center ones are not, the center rail is not a through mortise, but because we can change the depth of the mortise, the length, we can say we don't want the dowel or the hole in it, we have a lot of control. And we're standardizing it. We're standardizing on the way we work. So you could see that that particular unit now is a single part with 2 solid bodies. One is the mortise and one is the tenon. And then using the attach tool, again, one of the features of our woodworking set, we can say select the face you're mortising on, and we just touch the face and that part moves to that face. Select the top of the joint, it moves to that, and then select the offset, we just touch on the actual stretcher and it centers it for us. If we turn off the visibility, you see that it's sitting in there. It's still not part of the stretcher, but it will be. Now, the other mortise or tenon is a little bit different. In Mission Furniture, normally a through tenon has a slight radius or rounding on the end as it protrudes, and because this is a I part, we have the ability of suppressing or not any of the features, and of course that fillet is one of those features. Again, full size is there, so no matter how thick the material is, we can adjust it. Again, we'll use an attach tool, and making it very standardized, it says select the face you're mortising on using the terminology that woodworkers know. Select the face to offset from the top, and then the face that we're drilling into, and you could see that the dowel actually is exactly where it belongs. Now, the whole purpose of this is ease of use, to be able to create this entire unit in under a half an hour, fully controllable, and out to machining. Again, we're not finished yet. We will move in that direction in a second, but obviously you see that all these pieces are accurately being displayed. Now that we created most of the individual joints that are necessary in the creation of this particular table system, the next step is, of course, to copy them to the other areas. And again, because this is a very regular table, we can pattern them. So again, normal pattern tool inside of Inventor will allow us to touch each of the joints and do a circular pattern where we will then tell it we want a set of 4, and it'll pattern all the way around that table. Even if it wasn't regular and we had to put them in individually, instead of it taking a minute, it'll take 3 minutes. But I did not have to actually build anything onto the fascias or onto the rails. These are independent items that will become joints in a little bit. And of course, standardizing the world of construction, and that could get down to the level of 32 mil systems and any of the other standards that each company has. Okay, one last thing that I need to accomplish here is to use the Sculpt Tool inside of our woodworking tools. And this is a variation of the Sculpt Tool that is inside of Inventor, but this does a lot more. It will now bind the positive shapes to the stretchers, and it'll cut the negative shapes into the legs. So if we look at it and look real close, you'll see that the mortises are done, and the dovetails, which are tapered, are absolutely dead on. So that if I had put glue in there and pushed them down, it probably would need no clamping. Yes, I know I forgot to put one in there, so please don't email me and tell me that. I know. But again, I just wanted to show that, yes, I could have done that also, but I didn't, and that's why you don't see a joint there. Again, another way of standardizing our world. So let's go ahead and fix that situation. So obviously, yeah, I did forget to do that, and whether I want to go back and redo it or do I want to just move forward, either way will work. So again, I'll just place the dovetail piece of hardware, library item, in the system, and then using the place tool or the attach tool, it's saying select the face I'm cutting into, select the top of the joint, and select the side of the member it's being attached to. And now it's done. So you've got a very intricate corner condition. That would be very, very odd for someone to try to figure out on their own. Not impossible, but time consuming. In this world that I'm suggesting as a possible alternative to the way you work with Inventor, these are library items. If you're an AutoCAD user, it's just like having a dynamic block. Insert it the same way. Everybody does it the same way. Everybody expects the same results, and it's consistent across the board. My experience working with Inventor users throughout the US is that the consistency, even at firms that doing the same work, sometimes is at odds. So now you're taking a look at a triple dovetail joint, okay? And the strength of the dovetail and the strength of this all happens when they all go together, meaning when they're all glued up. And again, here's a joint that most likely won't even need a clamp. Basically a slight tap on a taper, hits home, it's not coming apart. So we see the negative shapes. Well, how about the positive shape? Let's open up a fascia. Take a look at the dovetail, the tails on this thing, okay? That is not an added part. That's an original part. That's a full piece. It's not added. It's not a solid body. That is complete. And if we can machine it that way, if we have the machinery to do it, then we can almost make a Chinese joint here any way we want and have a very, very interesting, presentation, because if they were different grain colors and you wanted to accent that, and I've seen that at many of my firms, then it's very unique from a very simple design. Well, what about the mortise at the bottom, the double mortises, the through mortise and the blind mortise? Again, same thing. Consistency always, absolutely centered, but I believe pretty easy to do. And you can see with the pin, without the pin, it's up to the user. And then the individual part itself, if we look at that, that is not two parts. It's a single part, one solid body. Take a look in the browser, you'll see that it's a single part, and as it could be machined as a single part, whether this is solids or whether it's composite materials, whether it's going to be bandsawed, whether it's going to be on a router table, it really doesn't matter. It's just creating geometry quickly and easily. Let's put the table on top, take a look at the whole thing, spin it around, save it. So I do believe we have a pretty complete model here. Obviously we can start manipulating it and changing it. Customer wants a 72-inch outside diameter, or maybe he wants to split the table and have a leaf in there. All these things can be planned for. And if we plan for change, we're going to be so much further down the road where our engineering or our design costs are minimal compared to what they might be today. And if we standardize, and that's one of the key things I always think about talking to anybody, then we bring in new people and they basically build the way everybody else has been building. They already have a rule set. Now, I changed the model and you could see some of the things didn't seem to update. Well, all we have to do is sculpt one more time. It's like an update and everything goes back correctly in place. So again, control it completely. The joints are correct. The tolerances are correct. Well, they're based on what the need of each company desires and the machinery they're using. But you can see that we just increased one of the stretches, and of course that grew, but the tenons of course are the same. And it's fully adjustable as what we were looking at previously, including the fascia and the dovetails on the end of the fascia. So again, fully controllable models done in a fraction of the time that it takes some people to do today. And this was just an example, again, of hardwood furniture. But if we're talking about millwork, we're talking about composites, plywood, veneers, edge banding, millwork, windows, doors. I mean, I can go on, and the same methodology can be used and implemented for all these others. Bill of material, cut list. How much time do you spend, looking at the model and adjusting it? Items like hardware would be always considered purchase parts. So again, these are just some of the really nice features that can be had utilizing Inventor, especially the renderings also. Thank you very much for attending our session today. I hope you enjoyed what I presented. We definitely are interested in your comments. Our plan is to have 3 or 4 more sessions before the end of July, where we'll be at the AWFS show in Las Vegas. It's the woodworking show. If anybody's attending, please find us there. But again, if you have any comments or there are areas of Inventor that you would like to see, please email us. The address at the bottom of the screen, or of course call us. Thank you once again for attending our session.